Hi, my name is Adam Lobo. I am a Robotics Masters of Engineering student at the University of Maryland, and this is my autonomous robotic vehicle. One of my first semester courses in the robotics program was an autonomous robotics class. The class tasked me with a semester-long project to construct and program a robotic vehicle to navigate, perceive, and transport specific objects. Specifically, the robot was given a 10-foot by 10-foot arena space randomly clustered with different color blocks. The robot's job was to autonomously identify red, green, and blue blocks, one by one, in that order, and transport them to a 4-foot by 4-foot zone in one corner of the arena, shown here. This robot is controlled by a Raspberry Pi 3 and an Arduino Nano. The robot is actuated using 4 stepper motors attached to 4 wheels, powered by 5 rechargeable AA batteries connected to a motor control driver. The robot uses encoders to track the total distance it has traveled and an IMU to track its absolute heading angle. It has grippers that are powered by a servo motor used to safely transport blocks. It also has a Pi camera module used to perceive different colored blocks in the environment and an ultrasonic sensor used to determine the robot's distance from an object in front of it. The assembly of the vehicle took place in class over 4 weeks in the middle of the semester. It involved everything from assembling the metal frame of the vehicle to soldering joints and wires to configuring everything in a way that would allow the robot to perform at its best while providing easy access to certain parts that may need to be swapped or removed. There were multiple times throughout and even after the assembly where I had to take apart much of the robot and reassemble it again due to either something being assembled in the wrong way or place or something missing entirely. It was a great learning experience though, as I have never assembled a prefabricated model of this sort. Basic locomotion involved turning on and off current going into certain nodes of an H-bridge, depending on which way I want each motor to turn. To move the vehicle forward, the current going into the nodes of the H-bridge was configured in a way that allowed all the motors to turn forward. Similar but opposite logic was applied to move the vehicle backward. To turn left, the motors on the right side of the vehicle spun forward, while the motors on the left side of the vehicle spun backward, and the opposite was true to turn the vehicle right. Changing the duty cycle of the current traveling into the H-bridge linearly changes the speed of the motors rotate at, and similarly, the speed the vehicle travels and turns at. To change the state of the grippers, the duty cycle of the current traveling into the servo motor was changed. For my vehicle, a duty cycle of 5% corresponds to fully closed grippers, while a duty cycle of 9.5% corresponds to fully open grippers. Intermediate values correspond to linearly proportionate states of the grippers. Localization of the robot involved using magnetic encoders attached to 2 of the 4 wheels to track the total magnitude of the distance that the vehicle has traversed so far. I used it to drive forward and backward user-defined distances. The IMU tracks the heading of the robot with respect to the initial heading when the IMU program was initiated. I use this to determine what angle the robot is facing at any given time and turn the robot a certain number of degrees left or right or to a specific absolute heading. My robot needed to operate autonomously, and in order to do so, it needed to perceive its environment. The major perception required in this challenge was identifying different colored objects. As you can see here, I am demonstrating the robot's ability to identify the green traffic light and draw a green contour around it. And here you can see my robot attempting to identify the corners of this green arrow and determining from that the orientation of the arrow. But as you can tell, the corner identification is not consistently accurate, so corner detection was not used on my robot during the Grand Challenge. At this point, my robot was able to identify an object. Now it has to go and retrieve it. My algorithm for object retrieval involved moving forward a small amount to set the forward X direction after the robot was placed on the ground oriented toward the positive X axis. The robot then determined if an object was in the camera's field of view. If not, it would turn left in 45-degree increments until it identified the object in the field of view. It then aligned itself by turning right or left until the center of the object was in line with the center of the camera's view. This required the object's center point, determined by contours, to be within 20 pixels of the center of the camera's view. Once this was true, the robot moved forward in 12-inch increments. This was done so the robot could keep track of how far it has moved since the start, and so images can be taken and processed at reasonable intervals. This would continue until the robot reached the object. However, after every third step, the robot would realign itself if necessary. The robot would also open its grippers once it was within 2 steps of the object to be retrieved. The robot determined if the object was close enough to be within its grippers by the radius size of the contouring circle. The robot would then grab the object by closing its grippers. The next step in the grand challenge was to deliver the object, or block, to the construction site. My algorithm for doing this was to move to a specified point within the construction zone. This was done by first getting the current point, then using trigonometry and the Pythagorean theorem to calculate the absolute angle needed for the robot to be heading toward the point and the Euclidean distance between the 2 points. The robot would then turn to the necessary angle, then move forward the calculated distance to the point within the construction zone. Here, you can see my robot practicing moving between user-defined points within a 5-foot by 10-foot space. Every point that the robot moves it to is to be saved sequentially. During the retrieval, when the robot is not moving to specified points, the location of the robot during every step is still calculated, stored, and saved, so that the robot always knows where it is. The grand challenge required the robot to deliver a red block, followed by a green block, and then a blue block, one at a time, to the construction zone in that order. It would then go get the next red block, and so on until all 3 red, all 3 green, and all 3 blue blocks were in the construction zone. If the robot penetrated the 10-foot by 10-foot boundary, or got stuck in an infinite loop, the run was over. The robot had 2 runs to successfully complete the grand challenge mission. Unfortunately, my robot did not successfully complete the grand challenge and only managed to transport 1 red block into the construction zone on its better run. The robot pierced the boundary of the arena on both attempts, ending its runs. On the first run, it was due to the camera mistaking a screw on the grippers for a green object. On the second run, the robot slightly overshot its left turn heading toward the construction zone, causing its line of travel to cross the border. In hindsight, I would have refined my turning algorithm to reduce the heading error, which was up to 3 degrees. I would have also improved my color masking specifically for the shades of color of the blocks. I probably would have had my robot deliver the blocks closer to each other and to the center of the construction zone, rather than very spaced apart like I had programmed. Finally, I would have mounted the ultrasonic sensor to the top deck of the robot rather than the bottom, allowing me to make full use of it for detection of walls without nearby blocks setting off a false positive like they did with my sensor on the bottom deck.